Okay, hi everyone, I'm Loudas. I'm a graduate student at Princeton University, and today I would like to talk to you about how can we use the properties of host galaxies, of FRB host galaxies, to constrain their origin. So, as basically Kriti said earlier, we have found FRBs in star-forming galaxies, in quiescent galaxies, and one in globular cluster. And as Rui said earlier on, we can basically categorize the formation channels of magnetars into two different broad categories. The prompt formation channels, according to which the time delay between the progenitus formation and the emission is short, and the dynamical or delayed channel, according to which the time delay is large. Kriti analyzed the 51 localized FRBs host galaxies and showed that if you generalize a mock sample of galaxies and select them based on SFR, basically you can kind of reproduce the cumulative distribution in stellar mass. And she showed that you can do it across different redshifts. Motivated by Kriti's work, we wanted to basically build a new tool which is publicly available and you can all of you use it in order to simulate mock galaxies and compare with current and future data. And that's why we built this tool called GalFRB. What is this tool? Basically, it's a collection of modules for generating joint distributions for mock galaxies and compare it with future FRB hosts. How it works? Well, first of all, for each galaxy, you need to sample the redshift, the position, the distance from the observer, and the stellar mass. How you can do that? Well, you can use the stellar mass function, which is shown in this figure here, and you have to take into account the galaxy evolution, and therefore you need to use the stellar mass function that is redshift dependent. Here, different colors correspond to different redshifts, and this stellar mass function has been obtained by Joel, and is trained on Cosmos 2015 and HST data. Now, once you have a stellar mass and a redshift, you need to assign a star formation rate to your galaxy. How you can do that? Again, you can use the model by Joel, basically normalizing flow. It's basically a neural network, and sample star formation rate for given stellar mass and for given redshift. Here in this figure, I show you the probability density in the SFR stellar mass plane for a given redshift. And generally, this evolves with redshift, and we take this into account. Now, once you have the redshift, you know that galaxies will be fainter or brighter depending on whether they are star-forming or not, because they can be blue or red. And the mass-to-light ratio will change. In order to be able to say something about how bright the galaxy is, you need to know its color. However, we know that the color correlates with the star formation rate. For high star formation, you can basically have a wide range of colors because star-forming galaxies can be dusty or whatever. However, once you go to the quiescent population, which is down here and corresponds to low star formation, you basically end up with red galaxies. Now, if you have the color, you can extremely straightforward sample a mass-to-light ratio in the rest frame, in the frame of the galaxy. How you can do that? Again, you can use the model that is offered by Lee and Ledja and use the posterior distribution to sample the mass-to-light ratio in the rest frame for given color and redshift. Once you have this mass-to-light ratio, because this is in the G band, you have to convert it in the R band because we usually use the R band in order to study these galaxies. And the story doesn't stop there. You need to transform from the rest frame to the observer's frame, so at redshift 0. How you can do that? You can basically apply a K-correction model. Here we use the model that is offered by Kim et al. And basically it tells you that if you know the color of the galaxy in the rest frame and you know the redshift, then you can basically transform the mass-to-light ratio to the in the rest frame, from the rest frame to the lab frame or the observer's frame. Because if you know basically what's the shape of the spectrum, you can transform it to the observer's frame. So once you have the K correction, you obtain the mass-to-light ratio in the observer's frame. But you know the stellar mass for its galaxy, so you can solve for its apparent magnitude. And the galaxies that we use in order to find or to associate FRBs with galaxies, the galaxies that we use come from surveys that are magnitude limited. So you cannot see the faint galaxies, and you need to account for this selection bias. How you can do that? You can apply a magnitude cut in your sample that you have generated, and basically drop out all galaxies that have an apparent magnitude larger than this value. In this way, basically, you correct for this. Okay, so we have a package that can be used and create mock galaxy samples, so we're in business. We can compare with data. In this analysis, in this paper that was uploaded in archive last week, and you can find it online, we use the same dataset that Kriti used, and we generate two different mock galaxy populations. The blue one corresponds to galaxies that are selected based on star formation rate, and the green one corresponds to galaxies that are selected based on stellar mass. As you can see here, I have two lines for each population. The dashed line is the full sample without accounting for the optical biases, without correcting for the optical biases. And the solid one corresponds to the one after applying the magnitude cut. And as you can see, once I apply the magnitude cut, basically once I drop out all faint galaxies, I shift, my cumulative distribution function in stellar mass shifts to higher masses, because the low mass galaxies cannot make it, I don't detect them based on current samples. As you can see across different redshifts, the data which is shown by the black line here and the gray band gives you an estimate of the uncertainty. Basically, as you can see, we can reproduce the data with the SFR selected galaxies in all different redshifts. And then one difference that you can see between Kriti's work and our work is that we have managed to basically bring the prediction of the SFR selected galaxies closer to the data by accounting for difference in the mass to light ratio between star-forming galaxies and quiescent galaxies. We basically used a more sophisticated mass to light ratio prescription and found that the galaxies will be slightly fainter, and therefore we will have a higher cut. We'll drop out a larger fraction in the low mass. So the conclusion from this, or the takeaway message from this study is that FRBs are most likely star formation tracers. And if you want to quantify that, and we did, we performed a KS statistical test, and we calculate the p-values. As you can see, for the SFR weighted samples, all p-values are larger than 0.2, which is 1 sigma, so they agree with the data. While the mass selected galaxies disagree quite well with the data. Their p-values are significantly less than 2 times 10 to the minus 3. However, I told you earlier that some FRBs are found in quiescent galaxies. So does this break what I just said, that FRBs trace star formation? Well, if you plot the probability density of your mock galaxies, which is shown here with blue, the SFR selected as optically corrected galaxies, if you plot their probability density star formation rate versus stellar mass plane, you will find that you enclose, or this sample contains a fraction of quiescent galaxies, naturally. And if you also plot the data, which is shown here with magenta, they basically kind of reproduce what you expect. So they lie in regions where the probability density is high. But the key message here is that your sample, even if it's SFR selected, will naturally include some quiescent galaxies. So just by finding some FRBs in quiescent galaxies, and without saying anything about its location or its offset, you cannot basically conclude that you need an alternative information sample. However, some FRBs have been found, one at least, has been found in globular cluster, which has basically almost zero star formation rate. So let's see what can we do with the current data and what constraints can we get as regards multiple formation samples. How can we do that? Again, we can use the GAL-FRB package to create a hypersample where a fraction of galaxies, XSFR, traces star formation or is SFR selective, while the rest of them are tied to stellar mass. So I have my SFR selected galaxies, most of them are going to be star forming, spiral galaxies. I have my elliptical, the quiescent galaxies these are mass tracers, and I combine them. So I create a mixed population. And I again plot the predictions in the same figure that I showed you earlier. So different colors correspond to different mixtures. For x SFR equals to 1, which is the yellow line, basically all galaxies are SFR selected, which is basically identical to the blue line that I showed you earlier. While for x SFR 0, you basically reproduce the prediction of the mass selected galaxies, or all galaxies are selected based on mass. And everything in between is basically a mixture. Even by eye, if you consider the uncertainty in the data, you can see that something like 50% mixture can be consistent with the data. And let's quantify that. Let's perform a KS statistical test for the different redshift beams. And this is what I have done here. Here I show you the p-value as a function of 1 minus x SFR %, which is basically the fraction of galaxies that are weighted by stellar mass. And as you can see, for 0, which means that x SFR equals to 1, all galaxies are SFR selected, the p-values basically are maximized. But if you want to ask the question whether this sample is consistent with the data, you need to put a threshold in the p-value, 10 to the minus 2, I used here, which is roughly 2 sigma. And as you can see, you can go all the way to 40 to 60% of mixed populations and still be consistent with the current data. So we cannot really put stringent constraints or strong constraints on what's the mixture, but this is one way that we can basically put constraints once we have a larger sample. So multiple formation pathways are still consistent with current observations, and we need more data in order to proceed. How much time do I have? 1 minute? Okay. So the main takeaways are that studying FRB host galaxies is a powerful way to constrain the proposed FRB formation pathways. The current data favors scenarios where FRBs trace star formation, such as the Young magnetar emission model, which was where the magnetar has been formed through core collapse of a massive star. The SFR selected flux limited FRB hosts can still contain a fraction up to 30% of galaxies below the star-forming main sequence, in other words, quasars and galaxies. And if you consider multiple formation channels, then a fraction of 40 to 50% of FRBs can be tied to stellar mass while still being consistent with current FRB host data within 2 sigma. If you want to learn more about our work, you can find our paper on archive, so you can scan the QR code here. And I encourage you to have a look at our publicly available package, GalFRB, and try to install it and use it. It's pretty straightforward to create your own mock galaxy samples and consider your own stellar mass function, star formation rate, mass to light ratio distributions, and try to reproduce our data or put new constraints once you have new data sets. Thank you for your attention.
Besides the star formation rate and mass, and there's also a dimension which is the offset.
Yeah.
Is it included in your analysis?
So, yeah, currently it's not included. I plan to include it in the package, incorporate basically posterior distribution in the offset and sample offsets and see if it's consistent with the data.
Right.
But currently I don't have it.
Yeah, even though the galaxy is a star forming, but the region is not. So the local specific star forming rate actually is more important.
That's true. Once the localization becomes better, which will be in the next few years, I think we'll be able to use the offset as a way to probe the formation channels. That's a good point.
Last graph that you showed a little bit of a trend with the redshift.
Here?
Yeah, this one here.
Yeah.
I don't know if that's statistically significant.
Yeah, so the problem with this redshift beam, and the reason that the slope is so smooth, is that we only have 7 FRBs in this redshift beam. So it's just a matter of increasing the number of FRB hosts.
So it means it's statistically not significant.
Yeah, it's statistically not significant, basically, because it's only 7 FRBs. If we go to 20 or 24, as you can see, then we can start putting stronger and stronger constraints.
Very nice talk. So, what is the forecast? Say we have 10,000 FRBs. What sort of precision would you get?
Yeah, I think with 10,000 FRBs, we will not have this kind of slopes. It's going to be super steep. Because the main reason that you allow for all these alternative formation channels, or for these basically range of solutions, is that if you bootstrap your data, which is how I basically obtained the error here, you see that it's quite high, quite large, quite wide. If you manage to find 10,000 FRBs within its redshift beam, then this is going to be literally the median. So, as you can see, all the predictions will be quite, far away from this median, and therefore, even a slight shift to the right will basically give you a p-value extremely small. So this is just an effect of low statistics. Low numbers.
It's very, very nice. How confident are you that the underlying inputs to Gal FRB are the ground truth?
Well, to be honest, we need to be more careful when it comes to star formation rate. That's why here we compare the stellar mass, because the way you infer stellar mass and star formation rate is by fitting basically the SED. So depending on what stellar population synthesis model you will assume and what initial mass function, you may get slightly different results. The stellar mass, because it scales with the luminosity, cannot be extremely wrong. You may have an offset, but not extremely high. When it comes to star formation rate, it can be, you can go extremely wrong. Basically, different SED models give you different values. And so we need to do better in terms of modeling star formation rate. For star-forming galaxies, we have ways to check the star formation rate, for example, the emission lines. So we can double check if it makes sense. For quiescent galaxies, the star formation rate that you infer from SED fitting is more like an upper limit and not the median. So here, in this figure, I say that, okay, we include this sample includes some quiescent galaxies. This is actually an upper limit because the star formation rate is an upper limit, and these points are weighted by star formation rate. If I go and set the star formation rate of this galaxy to be 0, then they will disappear from the sun. We need to do better in terms of SED, but that's a huge problem